So let's start. Today we are going to discuss about pipelining briefly. During the previous discussion, we have introduced pipelining where you actually try to split a task into several subtasks where each subtask is executed parallelly. Now, in computer architecture, pipelining is the same thing. In the previous tutorial, we took an example of examination copy check, where we have seen that a particular examination copy is divided into 4 subcopies, and each subcopy is being checked by 4 different, examiners. Now, in computer architecture, pipelining is the similar thing, where you actually try to divide a task into subtasks. So, roughly speaking, two popular pipelining techniques are arithmetic pipelining and instruction pipelining. Arithmetic pipelining, instruction pipelining. Now, in arithmetic pipelining, what happens, you see, you try to divide an arithmetic instruction. Arithmetic instruction. Now, arithmetic instruction is what? So, if you try to do something like A and C equals to A plus B, or float C equals to A plus B, then this is an arithmetic type of calculation, arithmetic type of instruction. Now, the point to be noted is that this arithmetic instruction should be executed in the arithmetic and logic unit, ALU, segment of the CPU. On the other hand, instruction pipelining, instruction. What is an instruction? Everything is an instruction. Whatever you ask your computer to do is an instruction being provided to the computer system. So we will look into both arithmetic and instruction pipelining one after another. So one thing I will try to be a little faster, because as we have short time in this semester, so I will briefly try to introduce the concept to you so that you at least grab an idea about how these things work. So how you can split an arithmetic instruction into several sub instructions and try to execute those sub instructions into several segments of the CPU. That is the point we need to consider. So here we have an example where it has gone. Yes, here. So you can see that you have two floating point numbers, x and y, where x is a multiplied with 2 to the power a and y equals to b multiplied with 2 to the power b. Now this portion of the instruction, a for x and b for y, are called mantisas. And next, on the right side, after multiplication symbol, you have the exponents. So on real ground, x and y can look something like this. X equal to 0.9504 multiplied with 10 to the power 3, y equals to 0.8200 multiplied with 10 to the power 2. Now, if you want to try add x and y mathematically, you cannot do it. Why? Because if you look into the exponent section, for x it is 3 and for y it is 2. That means x and y are not aligned, right? So first you have to align them, then you can add the mantisas and multiply it with the aligned exponent. That is the idea. If you want to do this using pen and paper. Now, From computational perspective, what through what steps a computer has to go if you want to solve this addition problem by using some computer system. First, these two variables, x and y, has to be brought into the processor or into the ALU, brought into the ALU from the memory. You all know that whenever you declare some variable, the data corresponding to the variables are stored into the memory system, not into the processor itself. At the time of computation, you need to bring those data from memory into the processor. Now, as this is an arithmetic instruction, it will be executed in the ALU segment of the CPU. That means, as a first step, these two variables should be brought into the arithmetic logic unit for the computational purpose. Now, once they are brought, as we were not been able to add them because the exponents are not aligned, the next step would be to align the exponents. Once the exponents are aligned, you can add them and deliver the result. If you follow and split the problem in this way, you can see that you can design your ALU in such a way that in segment 1, this is segment 1, first you will compare the exponents, and in segment 2 you will align the mantisas. You can see that before alignment the value of mantissa for y was 0.8200, and after alignment the mantissa of y has become 0.0820. So in the second segment, uh, you will align the mantisas in the ALU. In the third segment, you will add or subtract whatever the arithmetic operation is, you will do that thing. And in the fourth segment, you will adjust the exponents as per the necessity. By adjustment, I mean to say, if the problem asks to deliver the result in 10 to the power 2 format, then you have to adjust it. If it says to represent the result in 10 to the power 4 format, then you have to adjust your mantissa for the result in that way. So in the segment 4, you can adjust that and then deliver the result here. You can see that here the results are being delivered. So in a nutshell, you can see that in arithmetic pipelining, you can create your arithmetic and logic unit in such a way that you can attach several segments into the processor to carry out those different tasks. Now, what is the advantage of doing this? How you can achieve pipelining, or in common words, some degree of parallelism by doing this. So, if you think of a virtual situation where you have two arithmetic instructions, first one is a plus b, where a is, for example, say 0.9 multiplied with 10 to the power 3, 0.3 multiplied with 10 to the power 2. Then following the first instruction, you have a second instruction, say c plus d, where you have 0.8 into 10 to the power 7 multiplied with 0.5 multiplied with 10 to the power 6. Now, if you follow our course of action, your computation starts, right? So, at the very beginning, the A and B from our first example will be brought into this register sets. Exponents will be brought into this register or copied into this variables small a and small b, and mantissas will be copied into the registers cap A and cap B, right? And the computation goes on in segment one. So in segment one, for the time being, the the what I meant to say, the exponents for the first instruction a and b, 10 to the power 3 and 10 to the power 2, will be compared. And after doing the comparison, the result, along with the variables small a, small b, cap a, cap b, will be delivered or handed over, not delivered, handed over to segment 2 to align the mantisas. Now, the point to be noted is that when the first instruction and its related variables, related data are handed over to segment D, what will happen? Segment 1 is for the time being idle. I repeat, once the uh, exponents first instruction, that is a plus b, are compared in segment 1, and they are handed over to segment 2 for aligning the mantisas by following the exponents. Segment 1 is now idle, right? So what you can do by following the route of pipelining, while in segment 2 the uh, mantisas for the first instruction, that is a and b, are being aligned, you can introduce the second instruction, that is C plus D, into segment 1 to compare the exponents for instruction 2, that is C plus D once again. Now you can see how you are achieving some degree of parallelism here. Two instructions are simultaneously being executed in the processor. Instruction 1, that is A plus B, is being executed in segment 2, and instruction 2, that is C plus D, is being executed in segment 1 in the same clock cycle parallelly. And that is the idea of arithmetic pipelining, where you try to execute two or more different arithmetic instructions simultaneously in different segments of the arithmetic and logic unit. That is the idea. Now come to the instruction pipelining. Now, instruction pipelining is something which is a bit complicated than arithmetic pipelining, because if you look into the arithmetic computations, they are instructions, but it doesn't mean that instructions has always have to be arithmetic or logic type. Instructions can be anything. For example, if you write something like exit, this is once again an instruction. Now, this exit is not an arithmetic and logic instruction, but instruction itself, which is being given to the processor by the control unit, some command. So, how you can divide an instruction execution cycle into several segments. That is the idea. Now, once again, like arithmetic pipelining, if you observe carefully, for a particular instruction to be executed, at first it must be fetched into the CPU from the memory. Once again, I will mention that whatever program you write, at first they reside in the memory until and unless you invoke that instruction. Once you invoke an instruction to execute, it is brought into the processor or CPU from the memory. That means for an instruction to be executed, it must be fetched from the memory into the CPU. So in an instruction execution cycle, the first step can be thought of as fetch. So we can call it instruction execution cycle, where the first step is fetch instruction, where you where the instruction is fetched into the processor from the memory. Okay, fine. And in the next step, what happens? You see, once the instruction is fetched, now to the CPU, it is not meaningful yet. Why? Because to execute it, CPU must first understand what kind of instruction it is. For example, we have written a command exit here. That means you are asking the CPU to exit the current program. Now, on the other hand, if you write something like, as we did here, int c equals to a plus b, int x equals to c plus d, that means it is a kind of arithmetic instruction, right? Now, if you write something like this, if a greater than b, it is once again an arithmetic logic type instruction. This is a logic type instruction, right? Now, if you look into the nature of these different types of instructions, you can see that these instructions should be executed in the ALU portion of the CPU. However, this exit command will be executed somewhere else in some other segment of the CPU. So essentially, for the processor, it becomes a must to decode the instruction so that the processor knows what kind of instruction it is and in which segment of the CPU this instruction will get executed. Okay, now calculate the effective address is there in the third step. You can see it here. So why you need to calculate the effective address? Once again, to get into this point, we have to go back to the arithmetic pipelining. If you can recall the arithmetic pipelining discussion, we can see that in arithmetic calculation, there are operands, but in other kind of instructions, there might be no operand. For exit, we have no operand. Direct operands are missing here. So to execute this kind of instructions, the operand have to be fetched from the memory. Now, when we say memory, from the perspective of a particular instruction, the memory is a vast space, right? Now, the question which is obvious is from where into the memory the data should be fetched. So, the next step would be to calculate the effective address for the operands. That means CPU must know from where into the memory the values for the present variables it will try to bring, right? So once the effective addresses are computed, now it's time to dive into actual computation task. That means actual operands. That means these actual values have to be brought. So it is called fetch operand stage. Now in the fifth step, you can see that execute the instruction. Now once the operands are fetched, it's time to execute the task. That is, for our this example, it was a plus b. It will processor will try to execute the actual instruction or actual computational task. And last step is to store the result in proper place. Now, why? Computation is done. Why you need to store the result in proper place? The answer is pretty straightforward and simple: for future use, right? Now, you see, in CPU, the number of registers are limited. They cannot store the result from a particular computation for infinite amount of time. It, so for future use, the result has to be stored into the memory once again after the computation. So in a nutshell, we can say that generally an instruction can be divided into several substeps: fetch instruction, decode instruction, fetch operand, execute, sorry, then write back. Now you can see that I have omitted the calculate effective address point from here. Now both are correct actually. Why? Because in some textbooks or in some processors, you will see that uh, calculate effective address is implemented as a separate segment inside the processor, and in some other CPUs, it is done in decode instruction or fetch operand stage, depending on the processor. But the basic idea is same. In instruction execution, in instruction pipelining, a particular instruction is splitted into several sub-stages in such a way, or several sub-instructions in such a way that those sub-instructions can be executed in different segments of the CPU parallelly. So once again, let me try to visualize this using some picture. You can see that this is a block diagram of a CPU. Now, here you can see that there are several segments for this purpose. Segment 1, segment 2, segment 3, segment 4. For this diagram, segment 1 is dedicated towards fetching the instructions from memory. Segment 2 is dedicated towards decode instructions. Segment 3, fetch operand from memory. Segment 4, execute. Then you can see that they have not implemented any write back stage. That means with execution of instruction, write back is completed. Now, here you can see that there is a branch like thing. Now, what is a branch? Branch is something which we try to implement using those if else things. Now, you can think it in a simple way. If the condition is satisfied, this set of instructions will get executed, else those set of instructions will be executed. That is the idea behind the branch. And now let we try to dive a little deeper into how instruction pipelining actually works. Let we have two simple instructions. Int I equals to 0, that is instruction 1. Int j equals to 0, that is instruction 2. Now let me try to ideate this thing. As we have discussed, we have 5 segments in our CPU: fetch instruction, decode instruction, fetch operand, execute, then write back. So how you can take advantage of pipelining here to achieve some degree of parallelism, that is the main idea. Now the clock starts ticking. Our time starts now, tau 1. So you can see that as the clock starts ticking, that means clock means not the clock which is being hanged in our walls. It is the CPU clock. So with the clock starts ticking, the first instruction, that is instruction 1, is fetched into the memory, right? Now in the first clock cycle, you can see that other segments of the CPU are kept idle. That means there has nothing to do. Now, when the next clock cycle starts, that means clock cycle T2, before the beginning of clock cycle T2 and at the end of clock cycle T1, instruction 1 is already fetched into the memory, into the processor, sorry. Then next task for instruction 1 will be to decode. It has to be decoded by the processor. That means you can transfer instruction 1 to the decode instruction segment in the clock cycle 2. Now, when the instruction 1 is transferred in the decode instruction segment, you can see that uh, fetch instruction segment in the CPU is idle. So when in clock cycle T2 instruction 1 is being decoded, you can fetch it into the processor from the memory. So you can see that in the same clock cycle, instruction 1 task is going on instruction 1 and instruction 2. However, in different segments of the CPU. So in this way, by using instruction pipelining, you can achieve some degree of parallelism as well. That is the idea of instruction pipelining. Here now, with every theory, there we have some problems. And the basic problems which you can face in uh, instruction pipelining as a whole are the pipelining conflicts. You can have three kinds of conflicts here. First one is resource conflict, second one is data dependency, and third one is branch difficulty. Now, resource conflict is caused when two segments try to access the same memory location during the same clock cycle, right? So how this look like, say you have a memory location here, M, and you have two instructions I1 and I2, which are now in two different segments of the CPU and being executed in the same clock cycle. Now imagine what will happen if I1 and I2 both try to access the memory location M simultaneously in the same clock cycle Tn. There will be a kind of conflict, right? This kind of conflict is called resource conflict. Next, you have data dependency. Now, data dependency occurs in the situations where the next instruction depends on the previous instructions, right? So, how it looks like? It looks something like, say, in the first instruction, you have I equals to A plus B, and in the next instruction, you have I plus plus. Now, you can see that you cannot execute the instruction I plus plus unless the computation for I equals to A plus B is complete and it is written back into the memory, right? So you can see that these instructions are dependent on one another's data. So this kind of situation is called data dependency, right? And last one is called branch difficulty. So branch difficulty is something which you need to understand in a deeper way. Why? Suppose you have an instruction, if A greater than B, then try to execute statement 1, else try to execute statement 2. Now, as the clock starts and, sorry, here we have our fetch instruction segment. As the clock starts ticking, this if, let it is instruction 1, is brought into the fetch instruction segment, right? And in clock cycle tau 2, let me draw it with another color. Here we have decode instruction. So in clock cycle T2, what will happen? Instruction I1 will be pushed into decode instruction segment, right? Now try to figure out among S1, statement 1, S2, statement 2, which statement should be fetched here. You cannot actually say until the evaluation of this if statement is complete. So that is the idea of branch difficulty. It means that you cannot fetch the next instruction here. So why you have such kind of problem here? Because of this branch. This core segment is trying to create two different branches in the program. If the condition is satisfied, this branch will be followed. If not satisfied, that branch will be followed. That is the idea. So this is called branch difficulty. So yes, so for data dependency, some solutions are proposed. They are not foolproof indeed. In computer architecture, you don't have any solution which is complete for every situation. Two common techniques which are being used to minimize, not to solve, to minimize data dependency problem to certain extent are hardware interlocks and data operand forwarding. So, and delayed load as well. So, what are hardware interlocks? So, hardware interlocks and operand forwarding are depends on the CPU itself. How? When some operand or memory, where it is, yes, when some operand, say I1, is trying to access the memory location M, it will be locked by this instruction I1 for the time being. So, how long this lock will be kept until I1 is done with memory location M. That is hardware interlock. Now, the next thing was operand forwarding. By using operand forwarding, what happens? You see, you don't wait for the write back step to get completed. Why? You can see that when you are in the execution stage, the result is already available in the processor, right? So, if the next instruction is trying to access the same memory location, you can see that now after the execution stage, the first instruction is already have the desired value for the next instruction, which will be written back in the memory, right? So, one thing you can do is you can directly access it from the CPU registers itself. That means CPU registers can forward the operand from the memory to the next instruction rather than accessing memory. So this is called operand forwarding. And last one is delayed load. Delayed load is something which is similar to hardware interlocks to some extent. Here, what you do is when the CPU sees that I1 is trying to access the memory location M, it will delay the loading. That means fetch operand segment on I2 to some extent for some time until I1 is done with memory location M, because the CPU already knows that I1 is trying to overwrite the memory location M, which is being requested by the instruction I2 as well. That is the idea of delayed load. Now, for the last problem, that means branch difficulty, you can follow the same thing like delayed load, which is called delayed branch. Let me type it down here. Delayed branch. So, how the delayed branch operation looks like. So, you can ideate this by a simple example. So, we have discussed that you cannot actually introduce something from S1 or S2 until I1 is being introduced, right? Now, there will be other instructions in the program, right? Say statement 3, statement 4, statement 5, and so on, among which some of the instruction will not depend on this if else block, right? So by you can do one thing. You are trying to execute or trying to evaluate this if statement, and rather than trying to fetch the instructions in the if else block, you do what? You start bringing or fetching the instructions which are not interdependent in some way or other in the computations inside the if else block. In this way, what you do, you are delaying the instruction execution inside the if else block to some extent. This is called delayed branch, right? So that was some quick introduction to pipelining as a whole. It was quite fast. If you find any difficulty, I will later on update the recording of this class inside the Google Classroom. You can try to rewind it once again and go through the reading material. I hope this will make sense to you. So I should stop here.